me get that going, and no one else is in the waiting room right now. Let me get the screen share going, 'cause that's another thing to do. Get that. Okay, so I have the syllabus up because I had a couple of things to say about that. And two more people in the waiting room, of course, once I mention that. So I had a feeling that a question about contrast may come up. So I pulled up some things that we were looking at before. So this is a review from last week talking about R square for the model, change in R square for the model, and the role of the contrast statement. So can you all see this? I've got the Excel thing up that I made last time. Okay, so these are just fake numbers just to put in as an example. So this is a fake example that directly mirrors what I'm asking you to do in homework 5. So this homework is a hierarchical analysis, meaning that you add something in, you add some more stuff in, you add some more stuff in. And so I've troubleshoot several questions. Make sure that you're keeping your model as it was and adding stuff to it. So don't take the predictors out once you've passed a section, keep them in. So we started with an empty model. If you have an empty model, let's say that your residual variance is 200, your R square is 0 in the empty model because you have no predictors. You haven't explained any of it yet. We then add a single predictor. We're calling it predictor A. Let's say that your residual variance went down to 180. That's a 10% reduction. So 10% of the variability is due to the effect of predictor A. And we know whether or not that 10% R square is significant in two different ways. Because it's only one predictor, the test of that predictor's slope is equivalent to the test of that model. So when there's only one slope in the model, the test of the model, that's the F for the R square, is T squared as the test of the slope. So you don't have to do anything special to get a significance test of the R square. And relative to an R square of 0, that's a change of 10%. Where you have to use the contrast statement and the test statement in Stata, by the way, is in this type of situation where you've added more than one slope to the model and you want to test the joint contribution of what you've added. So had you added only one slope, you wouldn't need to do this because the significance test for that new slope would directly tell you if the change in the R square that it brought is significant. You have to do this whenever you're adding more than one thing. So in homework 5, it was two different versions of the GRE. And here it's going to be predictors B and C. So let's say that residual variance went down to 140, giving us a total R square for the three predictors of 30%. And relative to the previous model, that's a change of 20%. The role of the contrast statement in SAS, or the test statement in Stata, is to give you a significance test of that change in R square. Whether or not the new things you've added together work together to account for variance. And the reason that we have to do that is because it's not only their unique contribution that goes to the R square, but what they have in common that neither of them gets credit for. So it is technically possible to add two new slopes to a model to see that neither of the slopes individually are significant because that's their unique contribution, but yet as a set, they nevertheless increase the R square because of what they have in common. Okay, let's see, where'd you go, Katie? Are you with me so far? All right, so how do we get this change in R square from this step here, or how would we get the change in R square from this step here? The logic of these statements, so I'll just type in here actually. It said I have a note in here, we need to ask for the F test to be able to get these things. So it's these cells right here that we're after, the change in R square. If I was going to do the F test for B and C, that would be like this, contrast. Well, they put the label in F test for B and C, and then it would be the predictor, a 1, a comma, the other predictor, a 1, and a semicolon. So you're asking for one of each of the slopes, the comma is necessary to keep it from somehow adding them together to make one new slope, because you're still trying to get the idea that it's 2. In other words, numerator degrees of freedom of 2. The same idea in stata would be test, and then we put the slope in parenthesis and set it equal to 0, and we do it for the other one as well. There. And so the parentheses in stata do the same thing as the comma in SAS to delineate numerator degrees of freedom. So if the f-test you get back from this is significant, that tells you that the change in R squared that resulted from adding B and C at the same time is significantly greater than 0. Okay, Katie, does that work for you?
Yes, that helps. And then when you get the output in SAS, will it say like f-test?
It will say,
or contrast, like what?
Yeah, there will be a new table and it will have whatever label you've put in it on the
Okay.
left-hand side.
Okay,
And then you'll
perfect.
get, I think, contrast sums of squares, maybe something else, and there'll be a column for F and P at the end of it.
Okay, perfect. That helps. Thank you very much.
You're welcome. Other questions on this topic while we're here? Okay, to do this one, I would do the exact same thing, but swap out B and C for D and E. So to go from line 4 to line 5 to test the contribution of predictors D and E, I would do another test, just swapping out B and C for D and E. You don't have to use contrast to get the test of the model R square because that's already given to you. But if you were to list all 5 of the predictors on there, that would recreate the f-test for the model because that's what it means. All right. Other questions on this or homework 5 more generally, which is due Thursday? No, we're okay? Okay so far, at least. I had a look at the database this morning. It looks like we have a nice bimodal distribution of people who are mostly done or haven't started yet. So if you are in the latter, that's fine because it's not due till Thursday, but let me know if you run into any problems. The problems that I've helped folks troubleshoot thus far, I included example 5A and 5B as a way to illustrate the use of the contrast statement, but you're not supposed to follow what happened in those examples. You're supposed to follow the instructions and do a hierarchical specification that looks like this. I just wanted to show you some other ways that the contrast and test statements would be used to create custom f-tests that lump parameters together. So for instance, let me find, I pulled up 5B. This is the last model in example 5B. We didn't go over this in class, but I did a video on it. By the way, you've probably noticed my demeanor in the videos is a little bit different. You get like the Lisa reading bedtime story demeanor as the recordings in the video. And it's actually not too far off because my son right now is working his way through a college level textbook about weather. That is what we read to him at night. So I am learning about atmospheric pressure and adiabatic something or another. There's all kinds of new words, but it's like I'm reading to him in my nine-night voice about atmospheric pressure. And he likes looking at the figures and he doesn't understand most of it, but he just sits there calmly sucking his thumb, listening, to some textbook. So I just sort of like adopt the same demeanor, like how can I make this relaxing, like a day at the beach? We'll talk about example 5 and happy little trees and things like that. So in this example, which we are going to revisit in example 6 that we'll do this week, yes, great way to fall asleep, listening to statistics. If anyone has insomnia, I am here to help. So in this model, for instance, we have 5 predictors, and I have a couple examples of contrast. So they are in SAS, and here are the analogous statements in Stata. And the first one is a reproduction of the F-test for the model. So that's really here just for pedagogical purposes, or so that if you were somehow running a model where this didn't pop out automatically, you'd know how to get it. So if I list all of the predictors that are in the model, followed by a 1, separated by commas, or all 5 in different sets of parentheses in Stata, then I get the F-test for the model. Do the set of 5 predictors work together? The next one, the second one in the series here, is a special case that if you've taken analysis of variance coursework, or if you've taken classes where people use that terminology, this is what would be called the omnibus main effective group, the overall marginal effective group, so to speak. In this case, I have 2 dummy codes that are representing 3 groups. So this is dementia diagnosis, whether the participants who are older adults in this example are never going to have it, are eventually going to have it during the course of the longitudinal study that this is the baseline for, or who currently have it. And so that's what these contrasts represent, are group differences across these 3 types of people. Because there's 3 groups, it takes 2 sets of dummy codes. And so I'm lumping those 2 dummy codes together to create an overall test of whether group as that single predictor matters. So that's another use of contrast to come up with a joint F-test of the 2 contrasts that work together to delineate the 3 group means. And the same thing is down here. And then just to show that this procedure doesn't care what kind of predictor you throw in it, I did another one where I'm lumping together demographic variables. So I might have a question that says, what is the effect on predicting cognitive functioning of just knowing your gender and your age? How much does that carry as a predictor, as a set of predictors? So I have a contrast that lumped those together to be able to answer that type of question. So you can lump together effects of predictors in any different way that makes sense for you to be able to talk about how they relate to each other in the model. So this is a very general procedure that gets used in a lot of specific instances. Okay, questions on that? All right, and then actually, while we're on that topic, I am going to open up lecture 4 and do a very, very brief version of one slide that will answer your question, Pam, about how to code the groups correctly. Because I've opened this up, I think, in office hours, and so that way everybody who wasn't there has a chance to get it. 1 second. Come on. Close the window. All right, it's towards the end. So in your instructions for homework 5, I asked you to look at the happy example to figure out how to code your groups. And it is this slide, right? I know what I'm looking for. Where is it? Here, found it. So this is slide 38 of lecture 4. And my side panel won't go away, so I apologize. So the happy example, just to review, was a 5-category ordinal variable where the coding scheme that I have developed up in this left-hand corner is designed to give you the adjacent differences across the 5 categories. So moving from a score of 1 to 2, and then 2 to 3, 3 to 4, 4 to 5, because those ways of carving up that variable are going to be more useful than 1 versus 2, 1 versus 3, 1 versus 4, 1 versus 5. And the reason that these predictor variables that are going across in columns are interpreted the way that they are is because of what happens to the ones. So in each of these columns, it stays at 1 after that one has been passed. It doesn't go back to 0. And so what happens is that we have 0, 1 separating the 1 group from the 2 group, and 2 through 5 are lumped together. And so then the next contrast pops up and separates out 2 from 3. The next one separates 3 from 4, and then the next one separates 4 from 5. So Pam, I'm guessing what you did, because this is what everybody has done so far, is what's in the bottom right-hand corner, which is what we did in example 4, and what I asked you to do in homework 4 with the golf groups. The difference is the 0 that's highlighted in red. That's the one number that you need to change to make it work. Because in this coding scheme, the first variable is going to be low versus middle, and the second variable is going to be low versus upper, because that are the 2 groups that are lumped together. So we have the 0 for low, the 0 for upper lumped together. The second predictor comes along and splits them up. So if you replace this 0 in the bottom left-hand corner with a 1, then the second contrast will then separate out middle and severe instead of low versus severe, upper, whatever it is in this case. Okay, does that make sense or help? Okay, so this is the 0 to 1, that's what it takes. Now, to piggyback on something else that you said, though, is that you couldn't get it to work the way I had intended, but you figured out how to get it to work, right? So the way that you did it is not wrong, because if you get the right answers, by definition, it's not wrong. It's just an alternative way of representing the same information. The term for that we use in statistics is a reparameterization. That means another way of setting it up. Reparameterization. So this coding scheme gives you 2 out of the 3 group differences. The third is a linear combination. So if you created low versus, I'm trying to remember what the labels are, 1 versus 2 and 1 versus 3 as your coding scheme, you can still get 2 versus 3. You just need to write a statement to do it as a lin-com in Stata or an estimate statement in SAS. So, I mean, whichever 2 you want to put in the model, you can always get the third. So it's not wrong. But if you had set it up the way I had intended, then you wouldn't have needed to write any additional statements. So it's one more line of code. No biggie. All right. Other questions on any of this stuff from homework 5 or stuff that we had been talking about? Okay. Then, before I forget, we find the syllabus. A couple things. I have new material posted for this week and next week. I do not think we will get a chance to get into lecture 7 and example 7, and if we don't, I'm going to make a recording, because I'm going to be using this material as review in my spring class. So it will serve joint purposes. So I am teaching longitudinal models in the spring. It's listed as a PSQF 7375 special topics class. There's still room if anybody wants to come hang out with me. And this material will be prerequisite for that class. I also updated this course to reflect what actually happened this semester as opposed to what I had planned. Because, they're not the same in terms of the timing of things. And so if you want to have a record of what we actually went over and the timing of that, then you can download that. Sometimes professors want you to show them a syllabus of prerequisite material, particularly for this class since it's less well known. So that's available to you. The other thing that I wanted to mention is that you all should have gotten an email from Icon, Canvas, whatever the hell it's called, about course evaluations. Okay, I want to make you a deal. I'm wheeling and dealing here. So there's 2 deals. If this class, there are 23 of you. If I can get at least 21 of you to complete that evaluation, I'll give all of you 1 point extra credit. That's a whole percentage point. That's deal number one. So, and it's open this week and next week. So it closes before finals week. So you've got 2 weeks to do it. I'm glad you were going to do it anyway, but I'm trying to encourage participation in this to have a representative sample. Um, the downside of those evaluations is that this year they have removed our ability to add our own questions. And so historically, I have added more targeted questions about aspects of the class. And since they took away that privilege, I built a Qualtrics survey. So I'm asking you to do another evaluation that is custom, that is not something that is required by the university, that has questions that will actually help me to hopefully make this class better and my other classes better. And for that, if you complete that, I will give you another point of extra credit. So 2 points. And in that, the way that it's going to work is that you will get an email from Qualtrics asking you to take the survey. The survey is anonymous. I cannot see, there's no tie between your email address and your answers, but what I do see is a list of which emails have done the survey. So I will be able to tell for each of you if you have done a survey. I won't be able to tell which one you've done. So for that one, I can just give you the point if you do it. I don't have to have a completion rate of whatever. For the other one, I can't tell who's done it. I can only email the people who haven't. So goodwill of your neighbors. So that's my deal. 2 points extra credit for giving me feedback. And honesty is the best policy. I really do want to know what you think and if you have ideas on how this could go better since we're going to be zooming our way through the spring, then I'm especially interested in that. All right. Anything else, logistics, other stuff before we dive into new content? Okay, are you ready for something new? No, but you're here. You're here. It's going to be fun. Honestly, this next topic is one of my favorite things to teach out of everything that I teach because it's one of those things that once you see it, you can't unsee it. Like a magic eye poster. Do you guys remember those? Like the pictures where there's a hidden picture inside the picture. I use that analogy because everyone remembers those posters, except that I personally cannot ever see the thing. I have never actually seen the hidden picture inside that thing. But it's like that, though. Once you see it, you can't unsee it. And so I'm going to teach you how to interpret interaction terms to be able to examine hypotheses about moderation. It turns out that it's highly algorithmic, and once you learn the rules, you can do anything. And this is a topic that is very common in research hypotheses. The idea is that the effect of a predictor depends on other information about the person. So, does the effect of education on your income vary by your gender or your ethnic background? Does the effect of getting more training on performance depend on your personality or other characteristics? Hypotheses in research that are phrased as risk factors or protective factors. Have you heard that terminology before? That's moderation. The idea that like your ability to handle things, like the idea that for some people having a lot of stress has really bad impact on their mental and physical well-being, whereas for other people they can handle their stress better. The individual link between stress and well-being is different for different kinds of people. What is it that makes some people better able to handle stress? Is it their coping style? Is it their environmental resources? What is it? And so those sorts of things like that control how effective a variable is in a model. That's the idea of moderation. That's what we're going to do. Having children at a young age, yes. Yes. There are a lot of things that I'm able to handle better now that I've been a parent because you just have to. Otherwise, there's no choice. Indeed. So let's do this then. Let me go move this thing back over here. let's see, this is, here we go. Okay, let me move this thingy out of the way. So I'm opening up lecture 6. The beginning of this is not something that I'm going to ask you to do in homework, but it's something that I wanted you to know how to do in life. Okay? Because I feel responsible for that. So the first part of this is describing how you would generate predicted outcomes from a model to be able to illustrate your model findings. So how would you go about making a figure that would go into a poster presentation or a job talk, for instance? By the way, there's job talks happening this week for the school psychology positions. I would highly recommend that you guys go, even if you're not in school psychology, because exposure to how people give talks, what to do and what not to do, is something that is very beneficial. You'll see different strategies and how effective they are or are not. And how people use figures is a big one, because tables of numbers are not something that an audience is going to be able to use. A figure that illustrates your findings is. And so I wanted you to be able to have the capacity to make figures. And in order to make figures, you have to be able to make predictions. So that's the first topic in here. So there are 3 different strategies, at least, that people use to create predicted outcomes from a model. So you have your model predictors. You want to talk about what, your predicted cognition score would be for somebody who's this age, this gender, this level of physical functioning, etc., right? Or you may be actually wanting to make predictions for people in future samples. There are 3 different ways of going about this, and they are ranked here from most to least painful. The most painful would be to use Excel. So I used to have people do this for pedagogical purposes. This is where you would open up a spreadsheet, you would type in the parameter estimates from your output, right? Like your intercept estimate, your slope estimate. You would add in another column for the values of the predictors that you want to make, and then you would have another column that calculates the predicted outcome for each person. That's all fine and good. It makes it harder to compute standard errors, but it's also very error prone, because anytime that you are opening up a file and typing into it, something can go wrong. So we don't want that as a strategy to take with you into the reproducible research world. Second, and this is something you'll get a chance to practice in homework 6 to a little bit of an extent, and you've actually done this already, is to use estimate statements or LINCOM statements to generate predicted outcomes. So do you remember when I asked you for the group mean for age 3 and age 4 way back in homework 3? And then I asked you for the group mean for the control group and the mini golf group and the regular golf group. And I asked you, I forget what it was. I've done this a couple times on homework. This is what I'm talking about. The idea that you can write a line of code and generate a predicted outcome for any combination of the model predictors. In SAS, you can use the estimate command that you're already familiar with. There is a command in SPSS that's known as test that is available in only some of the routines. And hands down, Stata wins on this with their command that's called margins. I have not shown you margins yet, but you're going to love it. It's one of my favorite things about Stata. It's really, really slick. The third option is something that is most useful if you anticipate a very complex model, but you don't necessarily anticipate what all is going to be in it. And this is what I refer to as the method of fake people. I know it sounds crazy, but the method is you make up fake people and you add them to your data set. It's not cheating, I promise. I know you look skeptical. It's not cheating because you're not making up their outcome. You're making up the predictors. And every stats program has an option to generate predicted outcomes for every case in your data set. So you're going to ask it to generate predictions for your fake people, but because they don't actually have any outcome, they're not messing up your model. So it's just a way of hijacking the architecture to do something that would be more efficient than writing out all the different estimate statements. So I'll show you each of these things here in turn. So here's the most painful, the process in Excel, for instance. So this is the solution from the model that I just showed you at the end of example 5b, where we have age as a predictor. So the outcome here is cognition. It's a measure of crystallized intelligence. Fake data, of course, but based on real data. We have age, which is centered at 85. Grip strength is a predictor, which is a measure of physical functioning. So its grip strength is in pounds per square inch, centered at 9 pounds, which was near the mean. We have a binary variable for gender, men versus women, and then we have two dummy-coded contrasts for dementia group, where N stands for none, F stands for future, and C stands for current. And so this was my model. So one way to generate predicted outcomes is to type this estimate for the model parameters into Excel, have another set of typed in values for the predictors that I want to generate outcomes for. So in this case, the first three lines would be somebody who is age 80, because age is centered at 85, and then grip strength is centered at 9. And so I'm generating a prediction for somebody who has 6 pounds, 9 pounds, or 12 pounds. And I'm holding gender constant at men and dementia groups constant at none. And so I'm making up essentially 9 individuals here that are designed to illustrate sort of low, middle, and high values of two of my predictors, age and grip strength. And where the 5s and the 3s came from is standard deviation of these variables. So this is very common in making these sorts of pictures, is to use plus or minus 1 standard deviation as your prototypes for what is low and what is high. Note that I am not making groups though. I'm not dividing my sample into young people versus old people or weak people versus strong people. I'm not cutting up the variables. I'm just coming up with like prototypical individuals based on the distribution of the variables. So I have my fake people here. I have number 3 here is to generate my prediction for each person. So it would be the intercept times their value for age plus their value for age times the coefficient for age plus their value for grip times the coefficient for grip, and so on. Rearrange those 9 values into the 3x3 configuration that I have for low, middle, and high for each of my variables, and then make this picture. So this picture is the end goal of this process. The idea that if I were giving a talk and I wanted to show how my model conceptualized the effects of age and grip strength, then I have, say, grip strength on the x-axis here, and the slope of grip strength is the effect of grip in the variable. So people who are stronger are predicted to have higher levels of cognition. And I'm showing lines for different kinds of people with respect to their age. And so the effect of age in this picture is shown as the vertical distance between the lines. So moving up and down the y-axis, the people who are youngest, the 80-year-olds, are predicted to have higher scores than the 85-year-olds and then the 90-year-olds. So the negative effect of age is shown by the gaps between these lines on the y-axis. The positive slope for grip strength is shown by the slope of the line on the x-axis. Okay, with me so far? All right, how would you characterize these lines? Do they look like they're all the same or not the same? There's a word I'm thinking of that starts with a P.
Parallel?
Yeah, parallel lines. Do you think that's a coincidence or not? Not a coincidence. No, because the way this model is phrased is that there is an effective age and there is an effective grip strength. And this is foreshadowing what we're going to get to. There's nothing in the model that says that the effective age depends on how strong you are, or that the effect of how strong you are depends on how old you are. There's none of that depends on caveats in the model. So the model predicts the same effective grip strength at all ages, which is why the lines are parallel. And the model predicts the same effective age across grip strength, which is why the distances between the lines are constant. So this is what's going to be known as a main effects model, in that each predictor has its own effect. There's no dependency or relation or interaction between them. So this picture illustrates that phenomenon. Yeah, no age by grip strength interaction. Cognition is the outcome in this case. Yep. So this works well if you're trying to teach people these concepts, but it doesn't work as well if you want to do this type of plot for, say, a whole bunch of different outcomes, right? So, Kaylin, I'm calling on you because you sent me an email. You have like 6 outcomes that you're interested in for a research project, and like 10 predictors, and a whole slew of covariates. Sound familiar?
Yeah, I'm doing the adverse childhood experiences, which are 10 yes/no, like binary dummy. And then I'm trying to predict adolescent relationship connection. Plus I've got controls.
So you have a lot of potential combinations of this, right? Do you want to spend the
and
next...
I was trying to do it a really hard way.
Well, do you want to spend the next 6 months typing shit into Excel? Yeah, I would. No, I wouldn't either. Yeah. So let's speed this up because we have lives to lead. So here's an alternative that uses programming to get the same result. And this is what you guys know how to do. And this is first in SAS, and then the Stata version is in a couple slides. So in this model, I am generating 9 estimate statements, which are those 9 different kinds of people, low, medium, and high for age and grip strength. So to do that, I need one of the intercepts. I need a -5 for the value of age, in this case, because I want it for an 80-year-old. And because I want grip strength of 6, given that grip is centered at 9, I put in a -3 there. And I've chosen to hold gender and dementia groups constant at 0 so that I can just focus on the effects of age and grip strength. So this is a lot of typing. It gives you this table that shows up down here. One advantage of these statements is that no matter what the model fixed effects are, these will always give you the right answer. You don't have to spend your time typing the coefficients and watching them change as you were to add things or take things away from the model. So in this table, I'm saving it. So this ODS output statement here saves this table as a data set. I'm then going to take the labels from the left-hand column and turn them into new variables for age and grip. So I'm creating a variable called age inside that table here and a variable called grip. And then I have sgplot in SAS, which makes my picture. So this is a way to automate a lot of the steps that you would have to do manually in Excel. But it still requires typing out all of these statements, which is a bit repetitive, but also still good for pedagogical purposes. So Stata folks, this is all you have to do. You're going to love this. So regress, you know this, and that this margins command, welcome to. What margins does is generate predicted outcomes, and you can specify a range of values. So whereas SAS requires one line per unique value that you're trying to estimate for a predicted outcome, margins and the at command allows you to do a range. So what this -555 means here is given to you in the comment right above. Start from -5, go in increments of 5 up to 5. So it's going to do -5, 0, and then 5. Likewise for grip, it's going to start at -3 in increments of 3 and go up to 3 and hold the other things at 0. So this one line gives me all 9 values, and you could easily change the range to give you even more. And then margins plot. It anticipates what you want to do with that information. I'm telling it then to take the predicted values that this statement is generating, fit the x-axis is grip strength, and it automatically builds the lines. So this is slick. I wish SAS had something like this, and I have searched in vain. It does not. So state of margins is awesome. Questions on this so far? Okay, but we see the same tendency in terms of parallel lines here. So here's your third option. And Kaylin, I would actually recommend this one in your case when you have to do the same type of analysis for many different dependent measures. You know what your predictors are likely to be, but you don't know in what combination they're likely to shake out. So this is fake people. This is something you would only need to do in SAS because it doesn't have the same margins capability. So I'm making a new data set. It's literally going to be called fake people. Input names the columns of the data set. So I have a person ID variable and then all of my predictors. I'm going to center the predictors here, and then I'm entering data. So I am making up the rows of the data set that would hold these prototypical values. I then merge my fake people into the real data set, and I run my analysis on all the real people and the fake people simultaneously. The fake people don't have the cognition outcome. So they're not going to mess anything up. They're not going to be used in actually estimating the model. But this line right here, output out, predicted equals y hat, and the standard error of the y hat, that is going to create a new data set in the work library called pred outcomes, and it's going to have a column that I've named y hat and another column that is the standard error, and that's going to give me the predicted outcome for not only my fake people, but for every other case in my data set. So this way, if you know in advance that you're going to want to show effects of certain kinds of predictors, like you know what low, medium, and high is on this control variable, you have people who had this adverse event, no or yes, like you can make fake people that are sort of the prototypes for whom you're trying to describe. And then no matter what happens in the model, you can use this procedure to generate predicted outcomes for them. So it's the most efficient out of all of these, even though it sounds a little crazy. And if this sounds like, what the hell is she talking about? No worries. You can always do this because you already know how to do this. But again, for life purposes, I wanted you to have these sorts of examples to follow. That's why. Because life is more than just this class. All right. Any questions on that before we change gears?
Yeah, so for the fake people thing, you're generating predictor values for the sort of people you'd want to make predictions for, right? And then
Yeah.
you're making predictions for them and checking and seeing, okay, these are the people I'm interested in, and this is what the model predicts for them.
These are the people I want to show in my plot.
Okay.
So like if I know that I want to show the effective age and I want to show the effective grip strength, I can run descriptives on those variables and figure out what a good low value would be as -1 standard deviation, a middle value is something close to the mean, and a high value as +1. So otherwise I'd have to go digging through my data set until I found people who had the right combinations. Like I need a young person who's strong, I need a young person who's weak, I need an old person who's strong. Like I may not have the exact combinations that I want to show, so I'm just making people up that have them.
Okay. Okay, so estimate stuff from the real data and then make fake data to see what your model says about so and so kind of people.
Yeah.
Okay.
Yeah, you could think of this as like if you had your model on a current data set and you wanted to generate predictions for a new sample.
Okay,
This is how you would do it.
got it.
Thanks for the question. So pictures are especially important if you're going to be talking about moderation. So that's why this is in front of all of what's to come. So welcome to interaction terms, my friends. You don't look as excited as I would have thought. It's cool, I promise. So this new thing up here in green, that's what I'm talking about. The idea that I am going to fit a slope for the effect of two predictors multiplied together to make a new thing. Have you guys seen anything like this before in your other previous coursework? Only one nod so far, maybe? Yeah. Have you seen like two-way analysis of variance before? Or a split plot analysis of variance? That's what this is. It actually is the same. It's just that it's not talked about in the same way. Yeah. But for those of you who haven't, that's fine, because that's what I'm assuming. So this is a basic example of what I would call a moderation model. The idea is that we can't talk about the effect, say, of X unless we know someone's standing on Z. The effect of X is no longer equal across people. It depends on some other interacting variable. And likewise, I can't just talk about the effect of Z without knowing where you stand on X. So the idea that the predictor's effect could be enhanced or dampened by another predictor in the model. That's what this is about. So this is known as moderation, not to be confused with the synonym of mediation. They are not the same. So we are talking about moderation here. Moderation is the idea that the effect of a predictor depends on another predictor. Mediation is the idea that the effect of a predictor is because of another predictor. So that's a different animal. What you're doing in fitting regression models with multiple predictors is actually mediation, just that mediation has a better marketing campaign and new vocabulary that goes with it. So this is moderation. So in this example equation up here, what it's saying is that the effect of X depends on Z, and the effect of Z depends on X. Mathematically, you can talk about it either way and have it be accurate. So there is no way to tell from a math point of view which is the moderator. But the way that people phrase research questions usually means that we're going to talk about one predictor as sort of the thing we care about, and then talk about how its slope varies for different kinds of people. And the variable that conveys different kinds of people is known as the moderator. So we can always fit these sorts of it depends moderation interaction effects. However, your previous exposure to them probably depends on which model framework they were coming from. So for instance, when I learned ANOVA, I learned it actually as an undergraduate at the University of Nebraska from Cal Garben. And I learned it using SPSS using the windows, like the GUI, right, where you click the boxes and all that stuff. So there's a box called fixed factors, and you can send your independent variables over into that box and click OK, and then your output shows up, right? I'd never wrote an equation in my life, right? I'm like, I know how to do this. Click, 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 got it. I didn't understand that what SPSS was doing for me without my input, by the way, was fitting a model that had all possible interactions included amongst my fixed factors. So if I had predictor A that had 2 levels, and predictor B that had 3 levels, and predictor C that had 4 levels, it was fitting up to a 3-way interaction of A by B by C, as well as A by B by C, B by C, and main effects of A, B, and C. All of that was happening for me under the hood without my permission. So if you are coming at these sorts of models from that perspective, you're not used to making choices because of the way software is about what to include. And usually people don't mess with the model. They interpret which effects are significant, but they don't like remove ones that aren't significant and then change their interpretations. It's like, this is the model, a fully saturated model as it's known. In contrast, if you were still in the ANOVA class and you added a covariate, now that terminology refers to a quantitative predictor in particular. The software does not let you interact that with any of your IVs. You'd have to figure out how to hack it to go into the custom model, but by default, you're only allowed a main effect. So the idea that the effect of your, say, control versus treatment, that effect has nothing to do with your standing on your covariate. The model assumes that it's called homogeneity of regression. The effect of the covariate holds across all of those independent variables. It doesn't have to, but that's what the software is doing for you. If you took a regression class, then nothing happens for you behind the scenes. You even have to make your own variables. So from a regression standpoint, there is no default as to how many interactions should be included or up to what order. You get to decide all of that. And like to be able to fit this model, you would have to make a new column in your data set that literally was the multiplication of X and Z and put in that new column as a predictor. So you don't have to do that in regressance data or GLM. We've already fit examples like a quadratic effect where we're able to define these things on the fly. So the point of all of this is that no matter what kind of predictors you have, and no matter whether you're thinking about them as covariates or independent variables or just predictors, you can fit whatever kind of interaction moderation model you want and whatever the data need. There are no rules. So this sort of siloed way of teaching general linear models makes it much harder than it needs to be, I think. Okay. So you're going to hear me start to shift my terminology, and so I want to spend a little bit of time on that. In this context right here, like up till last week, you would have heard me say that beta 1 is the slope of x and beta 2 is the slope of z. That sound right? Fixed slopes, right? Because down the road, they can be random instead, but today in this class, they're fixed. So I'd say beta 0 is my fixed intercept, beta 1 is my fixed slope for x, beta 2 is my fixed slope for z. Once you have this interaction where x and z are multiplied together and that interaction is given a new slope of its own, the terminology switches. And you will hear me talk about beta 1, say in this context, as a main effect versus beta 3 as the interaction effect. So fixed slope of a variable that also is part of an interaction term is called a main effect. And the rule for these models is that if you have an interaction term, say between x and z, you have to keep the main effect slopes in the model too. So even if beta 1 is not significant, and even if beta 2 is not significant, they have to stay. They have to stay in order for the interaction term to mean what it's supposed to mean, which is this idea of what is the effect of each variable. How does it change as a function of the other? Each variable's effect has to be in the model to start with. So there are only 4 possible kinds of interactions in the world. 4. And you know what? We've already talked about this. The role of a two-way interaction, so the idea that there's 2 variables that multiply each other, that's what two-way means. The role of a two-way interaction is to take each of the main effect slopes, so the effect of x or the effect of z, and the interaction of x by z is going to make each of those main effects either more positive, less positive, more negative, or less negative. That's it. Those are the only kinds you can have. Everything is going to be one of those 4 choices. In talking about how the main effects change, though, we can no longer talk about just beta 1 is the slope of x and beta 2 is the slope of z. Those descriptions are not specific enough. Once a predictor is part of an interaction, its main effect slope is specific to the other variable being 0. So there is a conditionality there that cannot be ignored in order to interpret these things properly. And this is confusing because it sounds a lot like a unique effect when you're holding something constant, but this is a higher level of specificity than just holding something constant. So I have a terminology sort of taxonomy that I hope may help with this. So once upon a time, do you remember back when we only had one predictor in a model, like homework 3? You know, at the time, I'm guessing like if you looked at homework 3, you're like, holy crap. And now if you were to get it out again, you'd be like, this is easy. I know how to do this. It's fine. But let's put ourselves back in that framework, right? Like the very first model that you saw that had one predictor in it, we had a fixed intercept and we had a fixed slope, right? And that was sufficient vocabulary to describe that situation. The intercept is always the expected outcome when your predictors are 0, and a slope is always the change in the outcome for a 1-unit change in that predictor. So what we are doing now is taking this idea of a slope, which is still 1-unit change in y for a 1-unit, or the change in y for a 1-unit change in x, but we are talking about it more specifically as to how it would be interpreted. So these are 3 kinds of labels that could potentially apply to a slope: bivariate marginal, unique marginal, or unique conditional. So if I had a model that had only one slope, like I have x predicting y, the end, the way that I would talk about the slope of x is that it is bivariate, meaning just the 2 variables, and that it is marginal, meaning that it applies to everybody. The fixed slope is one number that describes the effect of x no matter who you are. Everyone in the sample gets the same effect of x. And because it's only x and y together, it's a bivariate relationship. So that was what we did in homework 3 and to some extent in homework 4. Each variable took more than one slope to describe it, but there was only one predictor in the model. What you're working on right now is models that have more than one predictor. The idea that we're trying to ascertain for each predictor what is its unique effect after controlling for all the other predictors. So if a predictor is not part of an interaction term, like what homework 5 is doing, we would say that its unique effect is marginal. It applies to everybody. I have one slope that's for the effect of age. I got another slope for the effect of grip strength. I got another slope for gender, and so forth. And so the effect of age does not depend on anything else. The effect of gender doesn't depend on anything else. The effect of grip doesn't depend on anything else. And that's why the lines were parallel in the plots that we just made. The new thing, where I am headed in these last 2 weeks, is the third category. If a predictor is part of an interaction term, not only is its effect unique because it's controlling for all the other predictors in the model, but it's also conditional on the interacting predictor being 0. So centering is going to matter a whole lot in making sure that we can interpret these slopes correctly. And this idea that the effect of a predictor is conditional at the 0 point of the interacting predictor sometimes gets called either a simple main effect or a simple slope. And I will apologize for this terminology. I did not invent it. Coming up with the terminology system where the word is simple is not how you make friends, right? Because this is anything but simple. What they mean by simple is conditional. Specific to something is what they mean. So you will hear me sometimes put the word simple in there. I'm going to try not to. Conditional is what I mean. So let's practice. I have a, oh, come on. No, let's practice, and I shut the thing down. I am clearly not very good at practicing. I meant to shut down the presentation. It's thinking about it. And here we go. Pick up where I left off. Thank you. Move that out of the way. And here we go. Not that one. One before. I wanted slide 11. That's what I want to do. Now I'm going to type. So this will be a vocabulary exercise. You can play along with me if you feel like it. So first model, if I have something that looks like this, I have three choices for how I would describe the slope for W. Bivariate marginal, unique marginal, or unique conditional. Which one of those labels do you think this one is? Yeah, we can go 1, 2, or 3 since they're in order. This can be a finger question. Got a couple votes for bivariate. Got 1 vote for unique conditional. You might think unique because it's the only one, but the idea that we only have 2 variables in the story means that it's bivariate. So it's bivariate because it's just the effect of W on Y, the same as a Pearson correlation. And it's marginal because what this model says that the way we describe how W relates to Y is the same for everybody. So beta 1 that captures that relationship is the same for everybody. So this one is going to be bivariate marginal. Now down here, next model. This is similar to what we had before, but with an extra term in here. So I have a fixed intercept beta 0. That would be the expected outcome when W, X, and Z are all 0. I have beta 1 for the slope of W, beta 2 for the slope of X, beta 3 for the slope of Z, and beta 4 is my interaction term. So right off the bat, none of these is going to be bivariate marginal. This is no longer bivariate. It is quadvariate. Is that a thing? Call it multivariate is close enough. The point is that the effect of W is after controlling for X and Z. The effect of X is after controlling for W and Z. So each of these is competing for which room did they clean all by themselves. Go back to the analogy of This Is Us, which is on again tonight, I think. No, wait, it's on hiatus. It's not coming back until January. So you have time to get caught up. But each predictor is responsible for cleaning how many rooms that no one else cleaned. Like that's what we're trying to ascertain here. So this has got to be unique marginal or unique conditional. So W here. Here's how you know. Do you see W represented anywhere else in the model? Nope. That means it's marginal. So W is unique marginal. Beta 1 describes the effect of W for everybody. Doesn't matter who you are. Your slope for W is beta 1. In contrast, the effect of X. Do you see X anywhere else in this model? So that means it has to be, can't spell today, unique conditional. Because what describes the effect of X is now 2 different terms. They work together. So what's going to happen is that this beta 2 effect of x only describes the effect of x if z is 0. So if I plug in z equals 0 to this last term, it drops. So that's the only situation in which beta 2 all by itself describes the effect of x, is when z is 0. So I'm going to add that in parentheses, because when z is 0. So that's what this idea of, stop it, conditional means, or what simple is sometimes called. It's the simple slope of x, because it's specific to when z is 0. Okay, how are we doing? Likewise, beta 3 for the slope of z. Do you see z anywhere else in the equation? Yep. So that means it is also unique conditional, and the same idea but in reverse. The only time when the effect of z is given only by beta 3 is when x is 0 and this last term drops. So beta 3 is now the slope of z, specifically, conditionally, when x is 0. Nope. There we go. So the difference, w is marginal, because beta 1 is the only thing that describes the effect of w in the model. So beta 1 is the slope of w for everybody. X and z are conditional because they're each involved in more than one term. And so the term main effect that describes, say, the effect of x is specific to when z is 0. And likewise, the main effect of z, as it's known, is specific to when x is 0. Now here's the last one. This will be a bit tricky. I'll start you off. It's unique because it's controlling for everything else. But is the interaction term marginal or conditional? Oh, we got to vote for marginal. Oh, we got some on both sides here. Pam, you look very happy about this. Why do you think it's marginal?
Because it's the combined effect together, so that's different.
Yes, exactly right.
I didn't say that right, but
no, you're exactly right, because we're not talking about x or z, we're talking about their combination. So do you see anything else in the line besides beta 4 that has both x and z? Nope. Then it's marginal. Another way of saying it is that beta 4 is the interaction term for everybody. The only situation in which you would see a two-way interaction term as conditional is if there was also a three-way interaction term in the model where it was part of something else too. We're not going to get to those in this class, but I am getting to those in the spring, so you'll get a chance to play. So the terminology then, like x and z, these slopes right here, simple slopes or simple main effects or conditional slopes, you can think of all of those things as interchangeable. The unique just defers to whether or not there's other predictors in the model, which when you get to interaction terms, there always is going to be. So all of these effects are unique, but only some of them are conditional. The ones that are part of interaction terms are the ones that are conditional. That just means that when we talk about what the numbers mean on our output, there's going to be a lot more words involved. It's not just the change in y for a 1 unit change in x. It would be the change in y, for instance, for a 1 unit change in x when z is 0. And this one is the change in y for a 1 unit change in z when x is 0. And the job of this interaction term does two things at the same time. It talks about how the effect of x changes as a function of z, and it talks about how the effect of z changes as a function of x. Either way is correct. And so we'll get a chance to practice that next time. And my PowerPoint has lost its will to live, which maybe is a good sign that it's time to adjourn for the day. The angry hourglass is never fun. All right, questions before we wrap up? All right, then we will dive back into this stuff next time. You will note that on your reading list for this unit, starting in the last unit and continuing, is chapter 2 of my book. So this is the exception to me telling you you don't have to read for this class. I would highly recommend it, not just because it was 5 years of my life, but because it's me trying in as straightforward as a way as possible of explaining this shit. So I wrote it for people just like you. So I hope it will be helpful. And I am supposed to be working on a second edition of my book. So if you have any feedback for how to make it more helpful, I would be all ears in trying to figure out how to revise it. So, all right. Anything else before we adjourn? All right, then go forth. Stay safe, stay sane. See you Thursday. Let me know if you need
Thank
anything.
you.